All right, so let's try this one. Now that we have some experience, let's see if we can work this problem. Now, what looks different here between the previous problem we did? It's still a simple supported beam. So we know at A, we know the displacement is 0. We don't know what the slope is. We know at B, we know the displacement is 0. Again, we don't know what the slope is. The difference here is you've got a linearly varying load, right? And unlike the previous problem, we're not quite sure where the maximum displacement would be. You'd have to actually solve this problem to try to find it. Would you expect the maximum displacement to be to the left of the middle or to the right of the middle? Probably to the right.
Why?
Why? There's more load on the right-hand side, so you'd expect the maximum displacement to shift towards the part that has the bigger load.
You said it was like opposite. Last week you were like...
Frames are funny.
Okay.
Frames they're more two-dimensional. They're harder to predict. But beams are usually pretty easy to predict. So if you were to look for your zero load, you would want to look at values greater than half the span. Okay, with that said, let's do a little planning. We're going to need to find a moment equation. So again, if I cut the structure here at some distance x, do you want to work the left side or the right side?
Left side.
Yeah, I think it's a good choice. The left side is just a single triangle, whereas the right side would be a trapezoid. Probably going to be messy on its own, but it also even be messier with the fact that this distance would be L minus x. So we're going to go to the left, and then we'll need to know the reaction at A. So I'll assume that I have a reaction at A and B. And let's take this distributed load across the whole structure and place it with a concentrated load at an equivalent location. So what would be the equivalent concentrated load? What's the area under the curve? So it's a triangle, so it would be 1/2 base L times W. So this is going to be WL over 2. And the distance from the centroid to this big end is going to be what? Yeah, 1/3 the distance, and the distance is L, so this will be L over 3. So that's everything we need to be able to find our reaction at A. So if we come back over here, and now some moments at B, all right? So by summing moments at B, we should be able to find our AY reaction. So about B, our concentrated equivalent creates what kind of moment with this sign convention? Positive, right? So it'll be the force, WL over 2, times the distance, L over 3. And then the other component in the system is this AY reaction. And about B, it's going to create what? Negative moment. So it'll be the force AY times the distance L. So it looks like AY is going to be equal to WL over 6. That's not right. What did I do wrong? Is that right? Oh, yeah, sorry. I was thinking of BY, which is twice as big. I was thinking this would be 1/3, but that's what BY is going to be. So that's correct for AY. All right, so I'm going to come down here and draw my Freebody diagram for this little chunk of the beam here. So we just found AY. It was WL over 6. Remember, this is a distance of x. And then here's our distributed load. And then remember that what we're looking for at the cut is the positive bending moment. So now I got to get this little triangular shape. I got to find the area under that. So before I can get started, I really need to know what the intensity of that loading is at the high spot. Well, really, I just need to know the slope of this line. And we always know the slope is rise over run, so that would be W over L. And at some distance x, it should be Wx over L. And you can check that. When x is equal to 0, this little equation says that the loading is 0, which it is. At x equal to L, the loading should be W. You put an L here, the L's cancel, you get W, so it works. So now what becomes then the concentrated force and the distance? Well, I'll write these over to the side here. So the force is going to be what? Yeah, it's going to be, it's a triangle, so it's 1/2 base times height. So I'll just write it out explicitly. 1/2 base x times height Wx over L. And then if you do a little work there, you'll find that it's Wx squared over 2L. Now you can kind of check that too, because remember we already did this problem for x equal to L, right? And we found WL over 2. So if you put in x equal L here, you get WL over 2, so it works. And then what would be the distance, D? What's going to be 1/3 of the total distance? The total distance is x, so D will be x over 3. So now I've got all my pieces. So now if I sum moments about the cut, what do I have? Starting here, I've got the moment, and with right-hand rule, that's positive. My force F about the cut is also creating positive. So again, the force is Wx squared over 2L, and the distance D is x over 3. And then I have my reaction force here, which is WL over 6. What kind of moment does that create about the cut? Negative. So the force, WL over 6, times the distance of x. So that tells me that my moment expression is equal to, let's see, I got a W and I got a 6. So I'll pull that out. What am I left with? Well, this first term looks like I got x cubed over L. Is that right? Yeah, and that's negative. Does that look right? I do that right? I think so. Then this other one becomes LX. And if you look at this, a quick check of the dimensions works out, because x cubed, that's length, divided by L, that'd be a length squared. And then L times x, that's length squared. So you can add those together. They're the same order. So that looks reasonable. And we can check it too. What is the moment at x equals 0? It should be 0. So you put in x equals 0, and it's 0. And we also know that the moment at x equal L, here at B, should also be 0. And if you put an L here, you get negative L squared plus L squared 0. So they both check. So it seems like it's working okay. It matches the condition. So now we're ready to do our integration. So the slope is going to be the integral of the moment divided by EI. And again, we'll assume EI is constant. We've got this W over 6, so I'll bring all that outside. So W over 6EI, and then I'll have the integral of all the stuff left inside, which will be x cubed over L plus LX dx. So there's my statement. Now I just have to process it. So again, W over 6EI, that's my constant. what am I left with? It looks like I've got x to the 4th over 4L plus Lx squared over 2 and an integration constant. So there's my first integration constant, but I don't know anything about slope here. So I just have to let it ride. So we'll integrate it one more time. Displacement is the integral of slope. So let's integrate that thing. So our constant's going to stay the same, W over 6EI. So let's integrate that. Let's see, we got x to the 5th over 20L plus Lx cubed over 6. And then C1, so that's easy, C1x, and then a new integration constant, C2. So we're really looking at what is C1 and C2 such that this equation matches our boundary conditions. And the first one is that we know the displacement at x equals 0, which is A, is 0. You put in x equals 0 here, this term goes away, 0, 0. All I'm left with is C2, so that's 0. Now, is this always going to be the case? No. We're working some pretty simple problems now. There's going to be times where that may not be true. You will always know at least two things, either two displacements or displacement and a slope, somewhere in the beam. So we got one of them, that's good. The other one is that at x equal L, I'm also saying my displacement 0. So what do we have left there when I put L? So I've got W over 6EI. Let's see what this is. So I put an L here. I get L to the 4th over 20 and L to the 4th over 6. So I'll have to find a common denominator. I guess it'll have to be 60. So I'll have 3 60ths plus 10 60ths. You see that? When I convert this to 60, you guys see that? So this 1/20th will be 3 over 60. This will be 10 over 60. And then 10 minus 3 is 7. So I get 7 L to the 4th over 60. And then, of course, I've got plus C1 L. So I can solve for C1. So C1 is equal to, just divide everything by L and change the sign. So you get minus 7WL cubed over 360 EI. And my minus sign kind of got lost there in the front. Let me try this. I'll put it up top so you can see it. So this one would be quite nice. When you plug this thing into here and looking for common denominators, probably 360 is going to be your common denominator. But for me, you're done. You don't have to plug it all back in. Now, if you're working a problem, say, on Mastering Engineering, and they ask you what's the maximum displacement in the beam, you got a little more work to do, right? You got to go back to your slope equation, which is 4th order, and find some roots. Now, initially that looks pretty tough, but you'll notice that you've got a 4th and a square, so you do a little substitution here, and you can actually turn this into a quadratic equation. And then you should know the roots of a quadratic equation, and when you find those two, you'll find out that it's something like 0.557 L. It's a little to the right of the middle. And then you could take that value and plug it in here and find the maximum displacement. But we're not going to worry about that, especially on the exam. That's just a little too much. That would be, I think, brutal and inhumane. to force you to do that. If you can do this, that's the hard part. The rest is just, you could throw it in your calculator. It'll tell you the roots. That wouldn't be that big of a deal. Questions? You guys are really digging this, I can tell. You're gobsmacked, as they say. Look that up.